Hey there, ladies and gents. For this video, we're going to be discussing how to graph rational functions. Just as a reminder, rational functions are any type of function in which you see an x or a variable in the denominator of a fraction. Remember, rational has the base word ratio in there. Ratio implies fractions. So here is the general shape of what one of these things might look like. Not all of them will look like this, but they'll be pretty similar. Rational functions will have something called a vertical asymptote, and that is an imaginary line that the function will approach infinitely. So as this curve here goes down, it'll get closer and closer and closer, infinitely closer to this, but it will never cross it. Similarly over here, as this function is going up and up and up, it'll get infinitely closer to this line. It will never, ever, ever cross that line. We also have horizontal asymptotes. These are also sometimes nicknamed end behavior lines, because if I were to zoom out of the graph, it kind of shows me what is the overall function as I go out towards, forever to the left towards negative infinity, or forever towards the right towards positive infinity. What is my graph's behavior doing? Horizontal asymptotes are different in vertical asymptotes in the sense that we are allowed to cross over them. You won't always cross through your horizontal asymptotes, however, it is allowed. Vertical asymptotes you absolutely cannot cross over. Horizontals you can. So now let's discuss some of the anatomy here. First, we have something called removable discontinuities. These are also nicknamed holes in the graph, and that's anytime we have something that factors from the numerator and the denominator. If we see the same factor that cancels out, we would have one specific x value that kind of goes away. So for a graph, you would see kind of like an open circle on the curve. So that's a removable discontinuity. X-intercepts are anytime we cross the x-axis. Vertical asymptotes and horizontal asymptotes we've already discussed. We'll be going over how to find those here in a second. And by the way, this document is shared with you all on the course schedule. Essentially, x-intercepts appear anytime we have a 0 in the numerator. Vertical asymptotes appear anytime we have a 0 in the denominator. Horizontal asymptotes are kind of their own interesting beast here. In this class, we're really only going to be covering the top two scenarios. And what that basically says is if the exponent of the numerator is smaller than or less than the exponent from the denominator, your horizontal asymptote is automatically y equals 0. If your exponent of the numerator is equal to, my apologies, then you're going to take the ratio of the leading coefficients, and we're going to see what that means here in just a second. There are also possibilities for something called oblique asymptotes, and that's where instead of this horizontal asymptote being a horizontal line, it would kind of be a diagonal line, a slant asymptote. For y-intercepts, sometimes these will show up on the graph, sometimes they won't. If they do, great. If not, no worries. If you ever need to find the y-intercept, all you have to do is just plug in 0 for x. All right, so let's take a look here. I kind of mentioned this before, but with the concept of holes, let's say there's a hole in the graph, maybe right here, that would show up as a little empty circle on the graph. And that means we just have a removable discontinuity. So let's take a look at our first example. And as we're going through these, if you need to pause at any specific point, please feel free to do so. First thing I'm noticing, just right off the bat, is the exponents of my numerator and denominator are the same. That means my horizontal asymptote is going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator. So the leading coefficient is the number attached. Here it's 2 over 1, so 2 divided by 1 is just, well, 2. So my horizontal asymptote, sometimes you'll hear nicknamed the HASI, is going to be y equals 2. So I haven't even mathed anything out yet, and I've already figured out a piece of my puzzle. So I've got my horizontal asymptote at y equals 2. All right. Now let's get into our factorization here. Every time we do these, you always want to factor. Starting off, I want to look for a GCF, 2x squared and negative 8. Got a GCF of 2. And that'll leave me with an x squared minus 4. And from there, I can actually keep going, right? 2 times the quantities x plus 2 and x minus 2. These are called conjugate pairs from the difference of squares factor pattern. And down below, let's see, I need two numbers that multiply -6 but add up to a +1. That would be a +3 and a -2. With these problems, typically the hardest part is going to be the factorization. And we're already done. So now let's take a look at our criteria that we're looking for. The domain. Basically, what's allowed for x? Well, my domain restrictions are things that wouldn't be allowed. And for those, I look at my denominator. We've also called these excluded values. So for this one, x plus 3, I'd have a domain restriction that x is not allowed to equal 3 because if I plugged in, -3, if I plugged in -3 here for x, I would get a 0 in the denominator, which means I'm trying to divide by 0, which we can't do because if you divide by 0, the whole universe implodes in on itself and everything you've ever known or loved will then cease to exist. Similarly, x is not allowed to equal 2 because if I plugged in a 2 here, 2 minus 2 is 0, and same thing. RD, that stands for removable discontinuities. I like to call these holes in the graph. Holes in the graph occur anytime we have factors that cancel out. Well, right here I'm seeing an x minus 2 and an x minus 2. Those would cancel each other out. So the value that that has is going to be an x value of 2, and then we need to figure out, well, what is the y value? Well, to figure out that y value, I'm going to plug it into my simplified version. So after I cancel these pieces out, I'm left with this simplified rational. And I'm going to plug in 2 for x. Let's see, 2 plus 2 is 4, and I multiply by 2 out front, so that's going to be 8. My numerator is 8. Over 2 plus 3, well, that's 5, so 8/5. 2 comma 8/5. 8/5, that's about 1.6. So 2 comma roughly 1.5. Let's go right about there-ish, give or take. Okay, so we've got part of the puzzle completed yet again. Let's see, next in line, we've got our vertical asymptote, the VASI. Vertical asymptotes, you have to look in the denominator after simplifying, so we've canceled things out and we've already simplified. When would our denominator be 0? Well, that would be a -3. So my vertical asymptote is going to be x equals -3. Now, one thing that we should kind of be on the lookout for and be paying attention to, these two values for the domain restrictions will also show up as removable discontinuities or vertical asymptotes. So these two numbers we'll see again as either the x values for removable discontinuities or holes in the graph or vertical asymptotes. So I've got my vertical asymptote at -3, x equals -3, so let's go ahead and jot that down. So I'll put a dotted line straight up and down at -3. X-intercepts. These occur anytime we have a 0 in the numerator after simplifying. Well, after we simplified, a -2 would give me a 0 in the numerator. So my x-intercepts would be at -2, 0. -2, 0. Graphically, that would be -2 on the x-axis. My y-intercept occurs anytime, let me adjust the camera here, anytime we plug in 0 for x. Now, here it says after you simplify. You could do it right off the bat. You'll get the same value. It doesn't matter. So we're plugging in 0 for x. If I plugged in 0 for x right here, I'd have 0 plus 2 times 2, so that's 4, over 0 plus 3, so 4/3. Or I could plug in 0 right off the bat, and if I do that, anything with an x cancels out, so I'll have -8 over -6, and that reduces again to 4/3. So either way you want to look at it, doesn't matter. So 0, 4/3. A little side note to mention here, this might not fit on your graph. So 4/3 will fit on my graph here, but if I get something like -25, obviously that's not going to fit, so I don't always have to draw that. 4/3, that's about 1 1/3, so 1.333333. So that'd be about right there is my y-intercept. And now I have enough information to kind of predict what the shape of this is. I can clearly see that down in this area, I've got a lot of behaviors going on. So I'm going to go ahead and connect these dots, what I have so far. And I know the behaviors of asymptotes is that my graph will get infinitely closer to the asymptote as I move downward, and it'll start to behave like this horizontal asymptote as I go towards infinity. And here's where we have to use a little bit of logic. The other portion of the graph, again, it should look something like this, has to appear in one of these three remaining quadrants, if you will. I can automatically rule out this top one here because we'll never see a situation in which a function portion is directly above another function portion, because then it wouldn't be a function, fails the vertical line test. I know it won't be over here, because if it were over here, we'd have to have an x-intercept, and if there was an x-intercept, we would have known about it. So therefore, it has to take place up in this top corner. Now, I don't know specific values. If I really wanted them, I could plug in, say, x equals -4, -5, -6. I could get specific points, but I know that that's the general idea. The last bit of this is the end behavior, and that's where it's saying as x approaches infinity and negative infinity. Well, infinity means it's going to the right. Negative infinity means we're going to the left. So as we go forever to the right, what's the y value that we're getting super close to? Well, it's going to be the same for right and left side. We're getting super close to a y value of 2. So there's a lot of information presented on this. I'm going to go ahead and do a part 2 video. If you need another example, we're going to do number 2 from this worksheet. If you're feeling confident on this, then feel free to take a stab at a few of the practice problems that we've given you in class. As always, if you're stuck, do not hesitate to reach out via email, swinging before school, after school, and we'll get you through this.